Here's my semester one Fakie for significant figures. Take some notes, kids. You can use them on the test. Any digit that is not zero is significant. And I want to point out that in this case, a trailing decimal zero does count. So that is 5 significant figures. The only reason to put a trailing decimal zero in there is because you measured it and it did succeed in being measured. You did measure it. It does count. It is reliable. So that is 5 reliable measured values. That is 5 significant figures. On the other hand, these zeros at the beginning were not actually measured, and they're only there to put the decimal in the right place. So these 3 do not count. Any zero in the middle does count, because if I can measure these smaller ones, certainly I can measure that one, and sometimes you just get 0. So this is 4 reliable measured digits. That is 4 significant figures. And this one is much the same. It has a 0 in the middle, so that is 3 reliable digits, 3 significant figures. Putting numbers into scientific notation uses the idea of significant figures in that we're not going to include the ones that are not significant. And another point I should make here then is that these trailing zeros before the decimal, the invisible decimal here, do not count. They are only there to push the decimal over from the 5. We need it to be 230,500. And if we put the decimal there, it will be wrong, right? So we need zeros to push the decimal out to here, but these zeros were never measured. They are only there to push the decimal out to here. So we will not include them in our scientific notation. And for scientific notation, we use digit dot, a phrase I stole from somewhere, some other teacher somewhere. And so we'll get the decimal after the first digit. Now, it moved 5 spots to get there. So what we're telling the people is the decimal is not really here. It is 5 spots smaller than what you're seeing here. And that way we're not lying. We will push the decimal to digit dot. So it will go here, but really it's 3 spots smaller than what you're viewing. If you want to put it back in the real place, it is 3 spots smaller. So times 10 to the negative 3. Also, don't forget the units. In this case, the decimal will go there, and we need to put it back bigger by 2 spots if we put it back to the real place. There we go. So here is my addition here. Now, notice we have some missing gaps in the information, so to speak. I don't know what these digits here are or this one here. And so my second and third decimal columns are unreliable. I don't know what I'm adding in here. So both of these columns are unreliable, and I will round them off when I get down to my final answer. So add them up like you're in 4th grade math class, and then round off the ones that are unreliable because we don't know what we're adding in there. For multiplying, it's different. We will count the significant figures. This is 3 significant figures and 2. And we will choose the least of what we just said, which is 2. 2 reliable digits, 2 significant figures. And we will report 2 significant figures in our answer. Regardless of the decimal, no matter where the decimal falls, we will report 2 significant figures. And in this case, it turns out to be 1 decimal there. And centimeters times centimeters is centimeters squared. Same for division. We have 3 sig figs, 4 sig figs, so our answer will get 3 significant figures in the answer, 1, 2, 3, regardless of the decimal. When we're doing scientific notation, adding and subtracting, what we have to do is make sure that the decimals actually line up like they really, really should. So it's tempting to say, well, duh, 4 minus 3 is 1. But the decimals aren't really lined up because remember, we said that this decimal is shifting 2 to the left, and this one is shifting 3 to the left. It's really tempting to say that 4 minus 3 is 1, but remember, this is shifting 2 decimals left, and this is shifting 3 decimals left, so they aren't really lined up like they look here, and here I have it done. So I wrote it out the normal fashion here, but what we have to do is make sure that these exponents are the same, and it's easier if you take the smaller one and change it to be the bigger one. And remember, here's a phrase that I would write down. Bigger is less negative. So the bigger one is less negative, which means that the smaller one is more negative. So I'm going to take the smaller one and change it to the bigger one just because it saves times later. So I'm going to make this 10 to the minus 2. And here's an important point. You can't just change that decimal on its own. This is getting bigger, so this part must get smaller to make up for it. So this is getting one decimal bigger. This must get one decimal smaller. So I get 0.30 when I do that. Now I have 4 minus 0.3, and I get 3.7. And the multiplier in an addition or subtraction problem in this case falls into the answer, just like 6 times 100 minus 2 times 100 is 4 times 100, isn't it? 600 minus 200 is 400. The multiplier, as long as they're the same thing, falls into the answer. In this one, I know the for 12, we're going to count the significant figures, which is 3 and 3. So we get 3 in our answer. 4 times 9 is 36. But remember, we get 3 sig figs, so we can say 0.0. And the exponents on a multiplying problem of scientific notation add up. So we get 8 plus negative 4, which is positive 4. But scientific notation is digit dot. So we've got to move the decimal to here, like that. This just got smaller by 1 decimal point, so this must get bigger by 1 decimal point. And E, capital E, means times 10 to the power of. It's just a shorthand. When we're dividing, we subtract the exponents. So negative 5 minus a negative 1 is negative 4. So 10 to the negative 4. The bottom number is the protons. The top number is the mass number. This is the protons, and this is the mass. The difference between them is the neutrons. This is the proton number. This is the mass number. The difference between them is the neutrons. So the protons is 8. The total number of particles in the core, the nucleus of this atom is 17. So the rest of the 17 must be the neutrons. Just do subtraction and you get 9 neutrons. On the periodic table, sodium is element 11. So that's 11 protons. The difference between these two numbers is the neutron, so that is 12. An element is defined by only one thing, the number of protons. Neutrons sometimes change and electrons come and go or change all the time. I mean, a lot, quite a lot. But if it has 9 protons, it's always fluorine. And if it has 28 protons, it's nickel. Cobalt plus 2, look it up. It has 27 protons, so the atomic number is 27 because this is exactly the same thing. This is just the English name for this concept. The mass number rounds off to 59, and just for this one thing, we said we were going to round it off to the nearest whole number. the difference between them is the neutrons. 59 minus 27 is 32. Now, the electrons would sort of normally match the protons, but this is plus 2, which means it is missing 2 electrons. So instead of having 27, it's missing 2, it has 25. Remember, these are positive and these are negative. So 27 positives and 25 negatives is what you need to make the minus 2 there. If you have 56 protons, go look it up. It's barium, bottom left. Now, we have 56 protons, which means that's a 56. The atomic mass, the decimal number runs off to 137 if we're going to use a whole number this time. The number of electrons is 54. That's 54 negatives and 56 positives. That means that the charge is positive 2. In this case, the number of electrons is 18, and the atomic number is 15, which means the proton number is 15, which means the element is phosphorus. So I know it's P, phosphorus. It has 15 positive protons, 18 negative electrons, which means the charge is minus 3. The mass number rounds off to 31, and then the neutrons is the difference of 16. The difference in isotopes is the neutrons, which means it has more items in the core, in the nucleus, so that also means they have a different mass. Everything else is the same. The protons are certainly the same, and that means the atomic number is the same, and the electrons are really based on the protons, so they're the same. And by the way, what I mean by an isotope is something like this. Carbon always has 6 protons, but sometimes it has 12 total particles, which is 6 more neutrons, or it can have 13 total particles, which is 7 neutrons, or it can have 14, which is 8 neutrons in the nucleus. But these are all carbon because they all have 6 protons. Every element past lead is radioactive. They're all radioactive in every instance, in every case, in every isotope past lead. And uranium is the last natural element. You can find uranium in the ground. That's where we get it. After that, though, after element 92, it's not in the ground. It was made in a lab in some fashion. Let's do these. Selenium has 6 valence electrons. Let's point that out. Remember, we go 8, 7, 6, 5, 4, 3, and then 2, 1 on the left, but it won't matter except for hydrogen out on the left. So selenium has 6 valence outer shell, outer energy level electrons. So I can go 1, 2, 3, 4, and I'm pointing at my 4 fluorines that I arranged around. Remember, the single one goes in the middle, the others are arrayed around the outside. And then I only used 4 of my seleniums, right? Valence electrons, I had 6, I used 4. The fluorines have 7 each. This column has 7 valence electrons. So I'm going to use 2, 4, 6, and 7, and the same, and the same, and the same. And so in between the seleniums and the fluorines, I have 1 from the fluorine, 1 from the selenium. That is a pair, and that is a shared pair. That is a bond. So I have all these bonded, but I had only used 4 of the 6 from the selenium. And so I have 2 more. And so I have an unshared pair. I have a cloud here. Now you need a molecular geometry chart, but go and look for 4 bonded atoms and 1 unshared cloud on a center point, and you find out that that is called sawhorse or sometimes seesaw. It's an octet violation because the selenium has 2, 4, 6, 8, 10 electrons, valence electrons on it. It is polar because go look at the electronegativity difference between selenium and fluorine on your electronegativity chart. I remember that this is a 4. And if we have a difference of 0.5 or greater, then we have a polar bond. So polar bond is greater than or equal to 0.5. And these are not symmetrical. This shape is not symmetrical, I should say. We can draw a line through the middle. It gives an unbalanced view. I can come around and help if you don't know what I mean, but we can draw an imaginary line through the middle, and we see that there's a greater pull toward the fluorines than the selenium and the cloud, and so we get a polarity away from the cloud. It doesn't matter where your cloud is. I drew mine up just because I think it looks good there, so it doesn't matter. And we draw it toward the negative side and put a little plus sign on the positive side. Let's do ozone. We get 3 O's, and look on your periodic table. It's in the 6 valence electron column. So we get 2, 4, 6, 2, 4, 6, and we know we need 2 and 4, and then I guess we could say 6 there. This oxygen has 2, 4, 6 valence electrons. It's not going to sit there and take it. It's going to get grabby. It's going to steal, but it has to borrow, or we should call it, to the middle. So pick an end and borrow to the middle. I'm going to pick the right end. It doesn't really matter. Because really, when the choices are equal, it chooses equally. And really, it half double bonds both directions, which we call a shared, which we call a resonance structure or a distributed bond. These cannot be polar bonds because obviously they have the same electronegativity value if they are the same element. The order of intermolecular forces from greatest to least is ionic when we have a plus or a minus item like H3O plus. Hydrogen bonding, which is H on N or O or F. Dipole, which means it's polar molecule. And if we don't have anything else, we have London dispersion forces or LDF. Everybody's tired of writing all that, right? A molecule can attract another just by being sort of plus on one end and sort of minus on another for, I don't know, a billionth of a second or something. So this does not have plus or minus. This does not have any H's, and it is not polar, we said. So the only thing left is that it is LDF. And if you look on your molecular geometry chart, because that is really a cloud, if you want to do that, maybe 2 dots there, then that is a bent shape. Boron is in the middle, H's are around the side, 1 valence electron each from the H's, 3 from the boron. That is 2, 2, 2. That is 3 shared pairs. That's all it can do. There's nothing else to borrow, plus boron is very bad at borrowing. It turns out it's very weak. So this is an octet violation because boron does not have 8 like you would think. It only has 6 valence electrons. That is trigonal planar. Look at your molecular geometry chart. And it is symmetrical. There's no way to find a plus or a minus side if you draw an imaginary line through it. So that is non-polar. It is not plus or minus. H is not on the N or O or F. It is not polar. So all that is left is that this has LDF. Nitrate is a bit of a special case. I'm going to do it over here. NOOO. The oxygen has 6 valence electrons. The nitrogen has 5, but remember we have an extra 1 electron here. So how about we just call that a 6 because we don't know where the extra 1 is. We just know that we have an extra 1. So why don't we just put it there just because it's easy. What I like to do with the oxygens around this outside is just put on the 6 and then see where I am. So then I have 6 more because I've used these 3 sets of 6. I have this set of 6 left, and I'm going to need 2 for bonds, 4 and 6 for bonds. And that leaves me with nitrogen only having 2, 4, 6 in its valence shell. And it's not going to like that. It's not going to take it. It's going to get grabby and it's going to borrow. But where does it borrow from? All the choices are equal. So it chooses equally. So just pick a side and borrow 2. I'm going to pick here just because of nothing and borrow it in there. So now nitrogen has 2, 4, 6, 8. But really, it was a distributed bond. It's really 1/3 double bonded in all directions, or it's a resonance structure. The name for it. Don't forget the brackets to say it really is -1. I didn't just mess up and put in an extra electron. Really, there's an extra one. What's the shape? Look on your molecular geometry chart for 3 bonded atoms and no extra clouds on the center point, and that is trigonal planar. And it is ionic, isn't it? Because it is a negative charge. This is symmetrical, and so we don't even need to look at the values. There's no way to draw an imaginary line through the center and get a side that's any kind of significantly different. And so this is non-polar. H3O plus is OHHH. Don't forget that. It's a plus, so it's obviously going to be ionic. IMF, isn't it? We have 6 valence and 1, so that's a total of 3, right? So it looks like 9, but we are missing 1 because it is positive. So really we have 8. So we need 2 and 4 and 6 just to get our bonds, and then we have another pair there, that unshared pair. So we have a total of 8 that we used. Oxygen has 8, hydrogen has 2, but hydrogen only ever wants 2 anyway, so that's fine. So it is not an octet violation. Hydrogen only ever wanted 2, and oxygen has 8. Look at the molecular geometry chart for 3 bonded atoms and an unshared cloud on a center point, and that is trigonal pyramidal. It's a pyramid. I know I have chromium and oxygen, so that's oxide because it's just O's. Now I know O likes to be -2, so that side is -6, isn't it? -6 total. And so the plus side must be +6 because you know the charges always add up to 0. It took 2 chromiums to do that +6, so they must be +3 each. So it is chromium, Roman 3, oxide. This is sodium, that is phosphate, and just look it up on the back. Phosphate. And that's it, because metals just get their name. And we don't have to say sodium 1 because sodium is always +1 because it's in the +1 column. Nickel 2 nitrate. Nickel is a +2. Nitrate, look it up on the back, is NO3 -1. So I know that the charges always add to 0. So I need 2 of this, sorry, +2, so that the charges add to 0. Aluminum oxide. Aluminum is in your +3 column. Oxygen is in your -2 column. And the charges, notice, usually go down and across. So the 2 went here, the 1 went there, invisible 1. And so what we can do is take the 2 down there and the 3 down there. Or you can think of it as like lowest common denominator type of thing. Where do 2 and 3 meet? At 6. Well, I need 3 -2's to be -6 on this side, and 2 +3's to be +6 on this side. And now the charges total add to 0. Tin is being a +4 here, and thiocyanate is a -1, so I need 4 of them to make this add to 0. For acids, if this is using sulfate, go look up on your ion chart, sulfate, it becomes sulfuric acid. Also, for some reason with sulfate and phosphate, the R's come back, so it's sulfuric acid, phosphoric acid. When there are no oxygens, then we get hydro something ic acid. So hydrochloric acid when there are no oxygens. You might make a note of to yourself about that. So hydrofluoric means there are no oxygens. So H is plus one, F is minus one. Put them together. That already adds to zero. Stop fixing it right there. Hypocarbonous. Well, hypocarbonous acid means there are two fewer oxygens than there would be if you were using carbonate. So we are not using CO3 minus 2. You know what? That is wrong. I just realized that's a 2 right there. This is carbonate. It ends in ATE, which would give us carbonic acid. Look at your acid naming chart. Carbonate would give us carbonic acid, but we have two fewer oxygens. We have CO, right? We do not have CO3. We have two fewer oxygens than carbonate. Carbonate is CO3. I have CO1, so that is two fewer. I'm using hypocarbonite, but with H's on the front. It is an acid. So if I'm using hypocarbonite, I get hypocarbonous acid. And the mistake was that this is minus 2, so there would need to be two H pluses on the front of it to make the charges add up to 0. Nitrous acid, the us means you're using nitrite, which is one fewer oxygen than nitrate. Nitrate in your chart, on your ion chart, is NO3 minus 1. But I'm using nitrite, so I'm using NO2 minus 1, and that means it can only handle one H plus on the front